Hey, how's everybody doing? My name is Aaron Bossert, and I'm going to be introducing you to a use case here where we'll be looking at real time entity tracking with a focus on geofencing and then also some behavior analytics based off of dwell times and proximity uh, uh, between different entities. So, as we get started here, just a quick introduction to the data set that we're looking at. This is a shipping data set that we collected over the course of about a week and a half and comprises some 600 million, give or take, points on the map. And what we've done is not just entered that data as individual points on the map, but we've also turned that into track data. And what that means is that we're now dealing with the data as individual entities, so each individual ship, and we can perform our analysis based off of that information. So rather than just simply saying, "Hey, at this particular point in time, I'm able to see that this ship is in this location," we can actually zoom back out and we can look at the ship based off of its position over the last few hours, the last few days, and into the future as well. So we can do a little bit of prediction there. First things first, just so you can get a sense of the scale of this data, here is a map representation of the data, and you can see here as we zoom in, we're looking at a fairly significant amount of data that covers the entire planet as far as shipping data goes over the course of that week and a half. Then moving back here, what we've done is we focused in on just one area of the map. And that's what's covered by this polygon right here in the Gulf of Mexico here in the United States. So what we've done here in terms of setting this data up, we are going to use SQL to connect to the data. So we're going to create some credentials, and then we're also going to connect up to a Kafka topic, which is running on Confluent Cloud here. This is a sampling of that data set that I just described to you a second ago, and this is now streaming in live once we have executed this load into statement here. So what we're doing here is we're creating a table for the track information, where we're keeping track of a timestamp, the continent of origin, the country of origin, the track ID, which is actually the MIMSI, the MMSI, which is a unique identifier that goes to each radio, each beacon within each vessel. And then we also have a navigation status, which says, is the ship moving? Is it docked? Is it at anchor? That kind of thing. And then, of course, we have a longitude and a latitude represented by the X and the Y coordinates, respectively. And then finally, we have the type of ship that it is. Is it a fishing vessel? Is it a military vessel, law enforcement, or something of the sort? So what we're doing now is we're executing this load into statement, which is going to start streaming that data into the database from that Kafka topic that we defined earlier. And you can see here that the data has streamed in, and we can zoom into this. We can take a look at all the different tracks that are associated, and you can see as we zoom in here, for example, in one of the kind of busier areas, we can kind of start to see what the ships are doing within these particular areas, whether they're hanging off to the edge over here, whether they're coming in and out of port, potentially fishing vessels that are moving around in these kind of erratic patterns right here. So the next thing that we're going to do is, now that we have this data ingested into the database and we can see where these vessels have been going, where they're going to, we're now going to treat these as individual tracks, right? So what exactly is a track, right? So a track is the combination of that entity ID, which is the ship identifier, so the MIMSI, along with an X and a Y coordinate and a timestamp, so that we can track this over time. And what we're doing here is we're just creating a simple track summary table so that we can get an idea of the tracks that we're looking at here. And for example, here we have this MIMSI 366997220. the number of observations that we have for it. So we have 1,810 separate observations for position reports from it. We can see how far it traveled. So in this particular case, 336 kilometers, and how many the duration of that track in hours, and then the average speed in kilometers per hour. We can see the the minimum latitude, the maximum latitude, so on and so forth. And one thing that we can do with this is we can kind of take a look at the data that's available here, and we can see, for example, the longest tracks that are available. And this is kind of a constantly refreshing view. So right now there's not that much showing up in there, but we do have one track right here that just disappeared on us and went somewhere else. But this updates every few seconds. So as you see long tracks, they get identified. They they show up in this view. So then as we move forward, now we can get into doing something with this data, right? So one of the things that we'd like to be able to do is we'd like to be able to define a geofence that we would like to keep track of which vessels come in and out of this particular triangle right here. What we're going to do is we're first going to define the geofence, which is what we're doing in this representation right here. Then we're going to create a new materialized view. And again, all of this is done via SQL, right? So there's no external data manipulation. There's no ETL pipeline to have to deal with. It's all handled within the database here. So we're creating this materialized view, which is recent tracks, and we're grabbing everything that has been seen within the last 4 hours. And then that's going to, you'll notice that we now have a subset of all the data, which is 102,000 separate samples that are going to go in there. And then from that, we're then going to figure out which ones are actually within that particular triangle. So the triangle that we defined up here. And from this, we're going to use a geospatial function, which is StTrackIntersex. And again, this is all within SQL syntax. And then from that table, we're going to grab the track ID, the longitude, the latitude, so the X and the Y coordinate and the timestamp. And then what that results in is a number of different tracks that entered into that triangle. Then what we're going to do is we're going to take that information and we're going to gather the entire track for each one of those vessels. And that's what this is right here. So you can see each one that had gone into that triangle, but it's more useful if we can see where they started from and potentially where they're going to. And you can see the track heads here represented by these diamonds right here. And you can see all the different vessels that have moved in, moved out, and moved around in the Gulf of Mexico, but all of them have transited through that triangle. So we're able to now look at that subset of the data that transited through that geofence that we set up, and we're able to get a good idea of where they started from, right? So this is, of course, useful to be able to do this, but it's not as useful as being able to actually take action based off of this. So what we do is we actually set up an alert, which is sent to a webhook. This could be sent to another Kafka topic, or it could be sent to something like Slack or an email or something of the sort. But essentially all we're doing here, and again, this is just in SQL, right? So no need for a complex ETL pipeline, no need for an external program written in Python or Java or something else. All we're doing is we're just saying, well, let's create a stream that refreshes every time there's a change based off of that materialized view that we created for the fence track. So this data right here, and every time a new record is added to that materialized view, we're then going to send that data over to this particular webhook, right? And this is what that ends up looking like. Granted, this is just a simple example, just using a demo webhook, right? So there's no real information in here. There's nothing, there's nothing beyond that. Just the fact that we're able to send out, here's 2 alerts that we sent to say, hey, there's a vessel that that went into our geofence. And then, of course, you can work with that data to then perform whatever analysis you may need, or alert someone, or take some other action, right? So all of this is well and good and useful. But another thing that might be useful as well is to be able to actually look at more behavioral type activity, right? So let's go and find all the instances where these vessels are perhaps sitting in one location for a long time. That might be of interest, or perhaps they're moving around a whole lot, but just in a very small location. So we look at those, and we look at the dwell time and loitering, and what we're calling dwell is when a ship just kind of sits still, more or less in the same position, stationary. And then what we're calling loitering is when that vessel is moving around a whole bunch, but just within a tiny area. So fishing vessels might display that behavior because they're going around just a very tight area where they happen to be picking up fish, right? So what we're going to do is create another materialized view for our analysis, and we're going to refresh it periodically. And then we're going to take a look at the output of that, and that's going to tell us which vessels are in the area. We can see how far they travel, both in longitude and latitude. We can also see the area that they covered within that time, as well as the length of the track. So when you look at the dwell time for this, we should have it on a map here. Shortly, it'll be vessels that are just kind of sitting still, which is not particularly interesting. But what we can do is we can focus in on vessels that are perhaps doing something a little bit more interesting in terms of loitering. Or I'm sorry, this is vessels that are sitting still. The next one will be where the vessels are loitering, and you can see here where these vessels, as we zoom in, they're really just sitting in place, right? They haven't moved anywhere. They're not going in or out or anywhere else. They just appear to be docked. And then we look at the alternate view of that, which is of course vessels that are loitering. And now we can see, as we zoom in, I think this one's a good one right here, if I remember correctly. Now you can see this vessel that over a long period of time is really just kind of, moving around generally in the same place, going back and forth. So this could easily represent a fishing vessel or a tugboat that is, kind of hanging out in the same area. So what this allows us to do is then to get an idea of what vessels are doing. And then if you want to have some more particular analysis, so not just did a vessel go into a particular geofence, but did it go into that geofence and then did it just sit there, for example? That might be one use case that you would have for this. You can then look at some other information. So for example, if we want to look at the proximity of vessels, so let's find all vessels that came within a certain distance of each other. That's another type of analysis, apart from just finding those that were, sitting still, that we can look at. And here we're doing, again, the same thing, right? So we're just creating a materialized view. This is all done via SQL that refreshes periodically. And we're now going to look for vessels that come within a certain distance of each other. And in this case, it's going to be within 2 kilometers of each other. So we run this, and again, very fast query that that goes across the data, and then we can then see this on a map as well, right? So we can zoom in, and hopefully it'll sit still long enough for me. There we go. So we can actually see here's 2 vessels that came in very close proximity to each other. We'll wait for it to refresh again. Now we can see another set of vessels that came within very close proximity. You'll see the intersection of their tracks right here. So they were both together in the same place and then moved off in a different area. So this is yet another type of analysis that we can do, and this might be useful in other cases. So for example, you might want to track illegal activity. So do you want to track vessels that come within a few meters of each other to transfer cargo, for example. This is a fairly common use case that might be seen in things like drug interdiction or illegal fishing types of use cases as well. So we can do that all with again with with SQL commands. There's no need for complex ETL pipelines. We can kind of all do this within the database, and at the end of the day, these materialized views are visible. We can do whatever we want to with that data, right? So we can we just simply list it off. We can send it to a webhook or to an email address or something of the sort, whatever might be of use. So I want to kind of take a step back now that we've walked through this whole process and kind of go over what we've looked at, and then I want to be able to pause and take some questions and be able to dig deeper anywhere folks would would like me to expand a little bit more. So if you remember, we started with our introduction. We take a sampling of the data, which is covering just this area within the Gulf of Mexico. From our larger data set, which is worldwide shipping traffic. Then from there, we do a little bit of setup here. So we start streaming the data from a Kafka topic into our database. We create the table. Here's the load into statement, and of course, here's the end result being all those tracks that that have been ingested into the database. We looked at what tracks are. We looked at how we can see those as tabular data. We looked at those on a map, and then of course we dug into to the geofencing use case and how to view which vessels were coming into this particular triangle right here, and then various different ways of looking at that. Then finally, the last two things that we looked at were looking at dwell times and loitering, and being able to see behavioral patterns. So are ships sitting still? Are they spinning around in the same area but not actually going anywhere, like fishing vessels or tugboats, things like that. And then finally, we looked at proximity. So being able to see vessels that that came within a certain distance of each other, and how that could be useful. So I'm going to go ahead and pause right here. I know we have about another 10 minutes left within the presentation, and I wanted to accept questions if anybody has any. So I'm seeing a question, which actually not one that I was expecting to hear, but it's actually a really good question, right? Which is, what is the greatest vulnerability of geofencing? So to the extent that the geofences that I set up here are all manual, I would argue that there's really not a whole lot that you can do to hack that, other than having your turn off your device entirely, right? So if you turn off your beacon, then clearly we can't tell when something is going into a particular geofence or not. But interestingly, that's something that we can track as well, is we can actually look for instances where a beacon has been turned off, right? So does a vessel move along a set course at a set speed and then all of a sudden disappear and then reappear some time later, right? So that's something that we could also look in the same manner as we were looking at the dwell time and the loiter. So I hope that answers the question. And actually, it turns out of course the second question that I'm seeing here is would geofencing work if location tracking is turned off? So no, it would not. We would have to have some sense of that. But again, we can also track when a beacon is turned off, right? So you can determine, hey, here's a set series of check-ins up until a certain amount of time. Then we have a gap in collection, and then it resumes at some other time. So that's also something that can be of interest. So in terms of the next question here is how would geofencing work on QGIS? So to the extent that that I use tools like Esri, so ArcGIS Desktop and things like that. Yes, you can absolutely do this same analysis here, right? So within something like ArcGIS Desktop, we have the ability to display maps from the database directly. So all the server-side rendering that we're doing to display the maps that I just showed you can also be put into ArcGIS Desktop. You have the ability to run Python notebooks, so Jupyter notebooks within ArcGIS, which you could use to add in all the different SQL statements that I did for this analysis. So yes, absolutely. Another question that just came in as well was whether or not this can work in a tool like Tableau. And yes, we have a plugin for Tableau as well, which allows you to visualize the maps. You can also take advantage of everything that Tableau has to offer in terms of its visualizations. So all the different types of charts and interactions and filters and automations, data telling or data storytelling type tools that they offer as well. So I see another question, whether we have a library of pre-built geofences. Not so much, right? So that would be something that you would want to come up with, though it's very simple to do, right? So all you have to do is um, add in whatever areas it is that you want to cover. Those could be county type boundaries, which are publicly available information, which can be directly ingested into the database. So not a library of pre-built geofences, but you can supply your own very, very easily and be up and running very quickly with that. The next question that I see is what's the name of the software? So this is Kinetica, and which kind of segues into one of the other points that I had wanted to make was that we actually have a free cloud version where you can actually try out this exact same workbook. It's one of our example workbooks, so you can get access to the very same data that I provided. In the demonstration here, you can stream it just like I did here. You can look at it in the SQL Workbench with everything already built and put together, so you can literally just click on the play button and perform the same analysis that I did. You can alter it in any which way you like and kind of play with it, if you will. So if possible, I think we'll be able to put a link to that, but it's cloud.kinetica.com where that is. I think if you guys can still see my desktop, I'm not sure, but we can add that back in. I've also opened up a browser page to that. So if you just navigate to cloud.kinetica.com, you can sign up for free. This is a free cloud version of Kinetica, where all you need is just a login. You can go in, you can have a limited amount of data stored in there. And once you go through the sign up process, go to login. Of course, I already have a login created here. You log in, and then you can see your free account here, and you can log into the same SQL Workbench, that I'm running from over here. Same thing in that cloud version. So again, that's cloud.kinetica.com. And the mobility data, is it available for individuals? So in the sense that we do have a sampling of the data as part of an example workbook, yes, that data is available. You just create the account on cloud.kinetica.com, and you can have access to it right there. So it shows up as one of the example workbooks. So if we go to the workbench, for example. Oh, and of course, I would have to remember my username and password for this. I believe that's it. Oop. Okay, so we won't log into that right now, but it'll be the same thing. And when you go to the workbooks on the left-hand side of the screen, right here, then you'll be able to see that. Okay, so if there's no more questions, then I really appreciate everybody taking the time to listen to me, speak about this use case. It's something that that we're very passionate about here, and happy to see everybody's interest. So it's been great speaking to you. Take care.